going to talk about the Cauchy-Riemann differential equations of this spherical geometry. This has a context in generating variable resolution solutions like the geometry. This is the scheme of my talk. Straight away going to the scope of this talk. Like we are going to understand the Cauchy-Riemann differential equation in the spherical geometry and its relation to the complex function theory. So, which will help to develop insights on the solutions of this CR equations. And these are the solutions which are helpful in generating smooth grid transformations on the sphere, and it is useful in variable resolution methods. This is a background, and basically this set of the PDEs were introduced in the work by the pioneering work of Schmidt on variable resolution global spectral method. So, in this talk, like I won't get into the details of the variable resolution spectral method, rather focus on the geometry. That will be more generic and it can be used for any other techniques also. Yeah. So, the Schmidt's framework imposed two conditions, and one of this condition is this CR equations. This condition was imposed to preserve the structure of the primitive equation under the transformation. The details of the work. So, sorry, left. So, we consider mapping on the spherical surface, that is a sphere denoted by tau, and this is defined in terms of the spherical coordinates. Lambda is the longitude and phi is the latitude, and this is transformed into the lambda prime and phi prime. So, for the sake of convenience, the transformation can be split into the two parts, tau 1 and tau 2. This tau 1 relates to the transformed coordinate, that is like lambda prime, and to tau, that is lambda prime is equal to tau 1 and phi prime equal to tau 2. The inverse transformation is denoted by eta. Eta takes from the primed coordinates to the original latitude longitude coordinate. So, these are the conditions imposed by Schmidt. The idea is to preserve the structure of the fundamental differential operators. Like this is the scalar product of the gradients, that should again map as a scalar product of the gradient in the transformed coordinates, perhaps multiplied by a scalar function. Similarly, the cross, this is a Jacobian operator that also transforms into a Jacobian operator, and this is a Laplacian operator. The Laplacian also like transforms into another as a Laplacian operator in the transformed coordinates. So, the observation is that the primitive equations are indeed expressed in terms of these complicated operators. So, if you preserve this, the transformed system will also be similar to the original system with some scaling by the factor f. The advantage is that like when we do that, it is possible to reuse the existing numerical methods with minor modification. So, this is the calculus, like basically how this equation was set up. So, on the sphere, unit sphere S2, A is a sufficiently smooth scalar function. Then the horizontal gradient operator can be expressed as a vector and with this operation. So, the scalar, this is a notation of the transformation. The scalar function A when it represented in terms of primed coordinates is denoted as A prime, and then the gradient operator can be expressed as this form. So the idea is that, like, now this is the transformation matrix. This is the matrix M, that is a Jacobian operator of the entire transformation concerning the del operator under the coordinate transformation. This operator M can be expressed in the prime coordinates in terms of through the inverse functions eta, that is eta 1, eta 2. Now, to get these operations with those nice properties mentioned in this previous equations, that is like that conserving the structure of the scalar product of the gradients, Jacobian and the Laplacian, these are the conditions imposed by the Schmidt's framework. That is, this, if you look at the matrix M prime, the scalar product of the column vector 1 should be equal to the determinant of this matrix. Similarly, the scalar product of the column 2 with itself should be equal to the determinant, and the cross, oh, I am sorry, there is a typo here, there is no H there, and this scalar product of the first column with the second column should be 0. These things were named by Schmidt as Cauchy-Riemann equations. It's not clear, like from it won't be clear like why it was named as, it's not obvious like why it is named as Cauchy-Riemann equations. And this forms into a set of 3 equations, and what I found was that, like, when we like do some certain algebraic manipulations, this reduces into a compact form, a set of 2 relationship. Then, like, if I substitute this for the entries, and this is the Cauchy-Riemann differential equations. So the solutions of this transformations are the coordinate transformation which has this nice property. And how do we solve it? So if I directly try to solve it, there are many approaches. The one approach being which comes handy is the separation of variables, in which, like, we assume the eta as a function of lambda prime, and eta 1 is a function of lambda prime alone, and eta 2 as a function of phi prime alone. We get this solution. Interestingly, this solution, when you set L equal to 1 and retain C, that becomes a Schmidt transformation. So the Schmidt transformation is written in a different form here in terms of like arc tangent and tangent functions. So this will produce final resolution over the one of the pole, and the resolution will decrease as we move towards the other pole, and it's a smooth decrease in the region in between these 2 poles. If I set C equal to 1 and retain L, what I get is a high resolution tropical belt transformation. So this is a transformation which was used to produce a final resolution in the entire tropical belt, with the coarsening of the resolution as we move away towards the poles. I will describe some detail like how this can be used, because something is, if you look at this, the transformation I'm expressing in terms of the tau functions, that is from latitude longitude coordinate to the primed coordinate. Lambda prime is equal to tau 1 and phi prime equal to tau 2, that we have seen. what will happen, you could notice this, the tau 1 ranges from 0 to 2 pi L, whereas this, we know that the longitude is generally taken to be 0 to 2 pi. This is something special about this, something tricky here. Whereas the tau 2 remains within, is a transformation from pole to pole. How to utilize this when you have this? That is something will be interesting to see. Yeah, this is a point I mentioned. Typically, like if you use this becomes the lambda prime basically like is associated through the coordinate function, the spherical coordinate function. Like typically we have, this is a point in the 3-dimensional space, this is x, y, z. What will happen for, so this is a coordinate function. The many points of more than one point will go to the same point, the image. That is like say 0, for example, like 0 to 2 pi lambda is equal to 2 pi by L, and lambda is equal to 0, 2 pi by L minus 1, etc. all will go to the same point. So, it is a many to one image, and here we have to create a many to one to a one to one image. For that, a Riemann surface approach is taken. The Riemann surface approach is to make it one to one. So, here we create a domain for the lambda prime phi prime coordinate. The domain is called sigma, such a way it becomes single valued there. This Riemann surface is an L sheeted surface, which each sheet is a sphere itself and with a cut along a meridian. So, we saw that like it was a 2 pi L. So, the Riemann surface has a sheet. This is the sheet 1. This is a sphere with a north pole and south pole. This is the lambda, it's the meridian 0, and the 2 pi is removed actually. So, a point which goes around this sheet will not come back here, rather it will go back to the second sheet. This also has the same thing. Again it will go through these are the local coordinates of the sphere. Like that, this edge is connected, the lambda equal to 2 pi of the sheet 1 is connected to the lambda equal to 0 of the sheet 2, and so on. On the Lth sheet, like on the Lth sheet, the lambda L 2 pi is connected to the first sheet. So, this is a surface with along the transformed longitude, it has a 2 pi L periodicity. So, I am like, this is a description of what I said, I have written it down. So, practically like each sheet is a sphere, the transformed equations can be discussed on this spherical sheet, and any numerical method can be used for that. So, if we take a uniform distribution on each of the uniform distribution of point on each of the sphere, upon the inverse transformation, that will lead to a variable resolution distribution on the sphere. Any question?
If you add up the sheet, that means that she's. I understand correctly. The sheet is the entire sphere or the sector or the
yes,
north-south sector.
Yeah, the sheet is that like yeah, the one it is a branch of the Riemann surface. Basically, this we cannot like visualize in a Euclidean space.
Okay.
It is like that's a difficulty. we cannot visualize, like we cannot embed in a Euclidean, three-dimensional Euclidean space. The idea is that the poles are common for all the sheets.
But if you add up all the sheet, will you get the surface of the sphere as is?
No.
No, this is different.
No. Basically, we can set up a map from this surface to the sphere, which has a one-to-one correspondence.
And isn't L equals 1, I mean L equals 1 is just one sheet,
Yes.
that is the sphere.
Yes.
That is the sphere already.
No.
So I'm just curious about how you're going to go, because I mean obviously all you've done, what you have now is you've turned the problem of mapping a sphere into L times that problem of mapping for L spheres. So I'm curious about where you're going to go with this.
Yeah, L sheets. So, there's an alternate approach to solve on the sphere, basically. Like, when we are doing it, like we found that it's most of the the metrologists I've been talking to were comfortable with the sphere. So even to discretize on the Riemann surface is going to longer time. So there's a shortcut I used. That is to create a reparameterization. That is like the lambda prime phi prime as another coordinate system. There is a one-to-one correspondence between this. I want to use. This is a Riemann surface. Then I have this relationship using, so this is nothing but like the union of on L. That is like you have I'm sorry. So on, it goes up to so I can generate a sphere with the coordinate phi prime, which will directly like varying to 0 to 2 pi L. So this induces a new parameterization as follows. So how to like get this is that you take the lambda prime and phi prime distribution. We have to use this function. Typically for the sphere we will be using cos lambda into cos phi sin lambda into cos phi if I call this as sigma. For this I can use the sigma prime. So what we do is that we know this lambda is related, lambda is equal to eta 1 as per our definition and eta 2. So if we have to use this, actually hope, I don't know, all of you could see this, which I think I mentioned in the slides. If you take this parameterization function and given any pair of lambda prime and phi prime, that will identify a unique point on the sphere. So we can use this parameterization to solve our equations. So taking an uniform distribution on this space, like within the lambda prime and phi prime, would lead to a variable resolution on the sphere.
The sigma 1 looks very identical to the absolute Cartesian coordinate x, y, z. No, x, y, z.
Yes, x, y, z.
Yeah, so this refers to some kind of unique point on the sphere.
Sigma 1, you mean like this eta 1 or sigma prime?
Sigma 1.
Yeah, this function is same. This is same as this. The only difference is that instead of lambda, you will have this eta 1 of lambda prime. And we are referring to the sphere in terms of this lambda prime and phi prime.
So you're just kind of redistributing the grid lines.
Yes, like.
And so you've got a mapping that's a variation on the lat long grid.
Yes, it will like, yeah.
Yeah, so it's just simply bunching up you've got a change of coordinates and a bunch of coordinates.
This will do what we'll do is that, like, since the one thing will happen is that, like, since it is the interval length is different, the lambda prime is it's a 2 pi L. Phi prime is same as it's a minus pi by 2 to plus pi by 2. It's the same as phi. So there is no difference in the length, but there will be a difference in the length. Essentially, you will take L times more points than what we typically take in usual longitude coordinate. So this is a typical grid we get using that. You see it like there's a convergence of latitudes around the equator, and the additional points in the longitude also like add to the conversions. You get a smooth grid, okay, tropics. This is only possible because of using the Riemann surface concept, and which induced a reparameterization. And the resolution will decrease at the poles. So the pole is not a conformal point here.
Your resolution, latitudinal resolution decrease, but not observing.
Latitude, even the longitudinal resolution increases due to the length. So we want to keep it equal. So we will be actually like taking L times more points than usual. So that will increase the resolution in the longitude.
Question. Do you have any control about how dense you will be in the tropical latitudes and how far the points will be towards the pole? Is there any control about?
The control is fixed by the transformation. The stretch factor is the L. The L
So
will,
you can just increase the number of points?
yes, yeah, we can increase the number of L.
And then you would probably, if you double L, then you would get
The concentration
of
more.
nodes,
more.
but you cannot have, say, a smaller area of refinement around the
No.
pole and then
So do you, with this L, so you're wrapping more points around several times?
Yeah,
And so do points, I mean, in your kind of in your, I guess it's your lambda prime space, are points then not, points in physical space are not consecutively ordered with respect to the lambda prime space, is that right? I mean, are they sort of interwoven?
it's not interwoven. It's the spacing will be same. I mean, like it's like fixing this interval. This can be made uniform. This will be uniform.
Right.
But the question is about the physical point, the relation between the physical point and the image point. Are they all consecutive or interleaved?
It's consecutive. It should be consecutive because, like, if I choose, we can determine if n.
I mean, they're consecutive on each sheet, but when maybe I'm not understanding, I mean, that's very possible. When you impose the sheet, it seems like maybe what you're doing, or at least maybe one,
Sorry.
I'm sort of making up the story of what I imagine you're talking about. So you have these sheets that you kind of impose on each other, and they're consecutive on each sheet, but when you project the sheets onto each other, do the points then appear in different?
No.
I'm not understanding.
I think one sheet is just a segment of the sphere.
Yes.
Not so.
Yeah, I mean, like one of a loon. I mean, if you take a spear.
So it's just really, so
Yeah.
you're just stretching your
Yeah,
computational
loon.
domain and adding more points, and then.
So one of the loon will be mapped into this will map into a
Okay.
full sphere.
Um,
That's what happens. Like
So you're
the
just.
slice will
you're
map
just
to a full sphere.
scaling your computational space to bunch up the points in physical.
This is how it will map.
So is it necessary that the whole thing is symmetric through the equator? Say you are interested in some parts of the world more, so want the resolution in India rather than in the southern hemisphere. Is it possible to do that here, or must it necessarily be symmetric through the equator?
I mean,
As it's shown here, it's shown symmetric, but if you want to push the resolution, as an example, more towards India, is that a
possible
possibility?
actually. We have to modify the transformation bit. This transformation has to be modified. So this fixes the equator and the poles. So rather, like if you look at another function, it's possible to do that. You have to shift it actually. Equator has to be. It is possible, but I have not described that here yet actually, the full expression of
It's easy
it.
to see how you do it. Tau 1 and Tau 2 are separated, and you just have a different choice of tau. You separated your transformations for the different directions at the beginning. Made it easier to do that. So you can I mean, it doesn't okay, yes.
Okay. Yeah, to have separation basically. I mean, the lambda prime should be dependent on one function. Yeah, here it's you mean the separation of variables, you mean? Yeah, that was one solution we get it actually. There could be other solutions possible.
Another question I have is the sheet you described. These are the same width or same.
Yes, all of them are same. All the spheres are there. All unit spheres, copies of spheres. So that was a case study of the Cauchy-Riemann equations I had shown. Now the interesting thing is that this can be connected to the complex function theory, this differential equations. Though, if you look at the existing literature, it is not obvious. This connection is not obvious. The complex function, one thing is like in the complex analysis, the Riemann, the unit sphere is used as a geometric model. I mean, so to represent the points, like normally like the one is a organ diagram where like you have a UV thing. This is an organ representation, which is normally known. Other is a spherical representation for the complex numbers. So through stereographic projection, the complex plane can be mapped, the points in the complex plane is mapped to the points on the sphere. This this connection, people use this connection to identify, get some important insights. But Cauchy and Jalan actually used that fact to show that like the Schmidt transformation is a unique transformation in the, on the sphere, which is a one-to-one map. That apart, like as far as the Cauchy-Riemann differential equations, we cannot get a why it's called Cauchy-Riemann. Like it's not like it was not coming out of there. To do that, actually, like I'm referring to the Cauchy-Riemann equation mentioned in the previous slides, do a change of variable. This change of variable then brings into this form, basically. Now you could identify this as a Cauchy-Riemann equation in the standard form. So essentially, like what brings is that like this is a plane if you take x to be the UV plane to be something I think E dot 2. There is some hint about, like in one of the papers of Schmidt about this relation to the thing, but it's not at all obvious. It's obscure. And I actually did that substitution and like derived it, like it was getting into this form, and I'm happy that. Thing is that the solution of Cauchy-Riemann equation is well known. There's a lot of solutions known. I mean, every analytical function of the complex plane becomes a solution. So if you take, and this is a rich set, so there are a lot of functions available, and each function can be used in some way to generate transformations. That's an interesting thing about this. I think many possibilities exist when we see that. I also tried to figure out, map the Schmidt transformation through one of the analytical function as a case study. If I take the function to be simple z plus a constant in addition, when I apply this coordinate, what you get is essentially a Schmidt transformation, turned in terms of lambda prime and phi prime coordinates. I have to use a m into z to get is what the high resolution tropical belt transformation. So these are some of the immediate examples I could relate to the complex function theory. So in a sense, we get a lot of new insight that using a complex function you can get a solution for this Cauchy-Riemann equations. That means there are many solutions available, and that should be explored to create a conformal transformations for the sphere. So let's see. So summary of it, and the connection between the complex function theory and the Cauchy-Riemann equations of the spherical geometry is established. Analytical functions of the complex plane can use to generate solutions of the CR equations. We have shown that like the Schmidt transformation and HTBT are related to elementary complex functions. So, thank you.
Thank you very much. I think that was quite challenging for us. Any complex function. Any other questions, Sean?
Have you mapped the meteorological equation to this geometry? Have you solved?
Yes, like I mapped these equations into the using the reparameterization map actually, and solved them.
And do you have any result?
Yeah, I have a paper in JCP.
What does it look like at the poles? I guess you have the standard pole problem at the poles.
Yes, I mean it's like it will get defocused there. The points will become very less.
Right, but there is still a pole.
Yeah, there is a pole.
Yeah, part of the practical application of it. So I understand that you do things a little different than the original thing of Schmidt, and that maybe enable you to increase the resolution more. But there are still kind of, when using it for practical modeling, some limitations. And I think the French have investigated it heavily, and they have seen a number of these practical limitations. And one obvious limitation is that if you have the refined area, you can't refine the vertical in the same area. You somehow are stuck with it. Is that true? That you do only horizontal refinement, and whatever you do in the vertical, it somehow needs to be global. So that would be a limitation.
The vertical?
Yes, in the vertical, yeah.
I'm not aware of it. I mean that the vertical resolution can be treated independently of this.
Yes, I mean, if you have the normal way of going to a refined model, then you have a refined area. You could, in principle, in the area you are interested more, also do vertically more level.
Oh, I mean,
so
like
that is a limitation. Is that a limitation for your approach? You can't do that. You must, whatever you do in the vertical, do globally. Or,
what do you mean is that like
You
if
mean
you are
whatever you do
increasing
in the
the
horizontal, you do throughout the column, throughout the depth.
yes, you
Which
can't.
is what most people, the way most people would do refinement, local refinement on the sphere. It's
Yes.
the whole depth of the atmosphere.
This is linked to spectral discretization, I think. This
I mean, if you want to increase the resolution of the vertical, I mean, wherever like corresponding to the higher resolution on the horizontal, you can also
Yeah.
as well increase the vertical resolution.
Yes, but it must be global, or?
Yeah, it will be global.
Yes, it must be global. So
transformation of the
yeah.
which
There are still limitations on how to use it. So if you would be interested to have a very high resolution somewhere, that can be only done with the classical method, I think, not with this one. Includes,
No, it should be possible. I mean,
but I think the French have finally not used only this, but then had a limited area model as well to do for very small areas, whatever they want in the small area. So it leads to a certain distance, that is my understanding, to a certain improvement, but not to everything what you want to do. If you want to have, say, a global model of 50-kilometer resolution, and over India one with 1 kilometer resolution, you may use this method to go to 10 kilometers, but you still need a 1 kilometer model at the end, I think.
okay,
So,
Toyota.
in this case, and that was actually what, after years of research, the French Met Office did. They had their own limited area model still, so it couldn't be So I think we are still at that point.
Are there any other round?
Okay, I have a question. I guess your transformation is a rotation invariant.
Yeah.
So in that case, we can flip the pole to other
Yes.
side and we can have a resolution,
Yes.
something like Canadians do.
Yeah. True. True.
You
I
can
mean, this
rotate, you can
one thing is
combine
that like this, even this equatorial belt can be pushed up through your translation, like that can do.
Any other comments? I think we've had quite a long session, so it'd be
Thank you.
good to get coming out. Thank you very much.
Thank you.